When we talked about quadratic equations and their applications, we talked about area of a rectangle, area problems, because area is two-dimensional, and so we might have a length times a width or a side times a side, and we end up with units squared, square units. Well, the same idea is behind the problems that we're going to do here that are applications of polynomial functions, or they have three dimensions, or are x to the third power equations, like length times width times height. So we're going to talk about some different box problems and how those apply to our polynomial equations. So the first one is an open box. It says that an open box can be made by cutting out squares from the corners of a 9 by 12 inch rectangular sheet of cardboard and folding up the sides. So we have in our diagram this sheet of cardboard, and it says that it's 9 by 12. And what they're going to do is cut out the corners, creating these little flaps. And they're going to fold it along these little flaps here because these pieces are now gone, right? These are all gone. They'll fold up these little flaps here and create a box with this as the bottom of the box. This is our bottom of the box right here. And these are the sides of the box when we fold it up. And so with that as our box, what they're asking is how can we maximize the volume? How can we make sure that we're getting the best volume out of this material? And so what we're going to do is kind of like we did with our area problems on these little squares. What we're going to do is take out some x unknown amount. So I'm going to take it out on both sides so that these are little squares, x by x squares. So all the way around we have these little x by x squares. And so along this piece of material, along this side, I've got 12 minus 2x. That's how long this little flap is going to be, 12 minus 2x. And down the side, I've done the same thing. I've got 9 minus 2x. 9 minus 2x. And so when I fold these flaps, this one is 12 minus 2x, this one is 9 minus 2x, and the height of my box when I fold this up is going to be x units. The height is x units. And so for my function for the volume, I've got length times width times height, or 9 minus 2x times 12 minus 2x times x, my height. Now, we can multiply all that together if you'd like, but just like we did on our area problems, if you want, you can type this into the calculator just as it is, and we can find our graph and our solution. Okay, so I've typed that into the calculator here. Let me see if I can flip that light off so it's not glaring on the calculator. There you go. Still kind of got a glare, but 9 minus 2x times 12 minus 2x times x. Again, the hardest part really on the TI is finding a good window for that. So on my window, I've set it from -1 to 10, and then scale of 1. And then the y's, I did -10 to 100. I'll do a scale of 10 there. And so let's look at our graph. All right, so there we go. So we've got our cubic function graph. We knew it was supposed to be x to the third power graph because we've got length, width, and height, or x times x times x. But in our situation, and we did domain and range to our particular situation when we were talking about area problems for real world situations as well. But in this situation, we are not going to have negative volume, and volume is our y value. So anything below this line is not going to be relevant to us. So we can stop right here. So it really just looks kind of like an off-shaped a little bit parabola. And so our x values going up, our y values, don't worry so much about the negatives. So it looks like we've got 1, 2, 3, 4, 5 marks, so about 4.5 marks over. And going up, we've got 1, 2, 3, 4, 5, 6, 7, 8, between 8 and 9, and those were by units of 10. So when we're drawing our graph, we're going to go 1, 2, 3, 4, 5. And these are just single units. And then going up, 1, 2, 3, 4, 5, 6, 7, 8, 9. So somewhere in there. And it was kind of offset, so kind of more to this side. And so it came up like this, it went down like that. Remember, it came down below and then it goes back up, but that part is not going to be relevant to our problem because that's where negative volume begins to occur. So for our domain, we're just talking about from where it began in a positive value. So this graph does continue over this way as well, but it begins at 0 for our situation, and then we need to find this intersection. So we're going to second calculate the intersection, the 0, go left and right, and it looks like that is at 4.5. All right, so our domain is going to run from 0 to 4.5. Okay, for our range, we're going from 0 up to our high point, so we need to find that maximum up there. Second, calculate the maximum. I wish I could get you a better picture of that. All right, and so we're going to go left and right of that highest point. And it says our maximum is at 1.697, comma 81.872. Okay, so our range is going to go from 0 to 81.872. Okay, so the question was to find the maximum volume of the box. So our maximum volume, remember, volume is our Y value. So our maximum volume is 81.872 cubic inches. And then this one also said find the dimensions that give you that maximum volume. So the dimensions are going to be the length, the width, and the height. Well, remember that our height is x. So the height is going to be 1.697 in order to get that maximum volume. So 1.697 inches by, and then we want to plug this 1.697 into these two equations here, these two, for our length and width. So we've got 9 minus 2 times 1.697. So 5.606. And the same thing, except with 12. 12 minus 2 times 1.697. So 8.606. So the dimensions of our box, 1.697 by 5.606 by 8.606 inches. If you multiply those together, you get 81.872 cubic inches. This next problem could be related to a couple of things. It says that a package may be sent by mail only if the sum of its height and the perimeter of the base is not more than 72 inches. So the size of the box determines whether or not it can be sent. Now, there may still be some mail delivery that will only take certain size packages. A lot of the smaller delivery companies used to limit the size of the package that you could send. The price became outrageous if the box was too large. So this was something maybe more important a while back, but it's still important to know how much it costs. The larger the package, of course, and the weight determine how much it's going to cost you to send it. So it's not totally outdated, but a little dated. But anyway, we'll go ahead and read through it. It says that a package can be sent by mail only if the sum of the height and the perimeter of the base, so the height plus the perimeter of the base, can't be more than 72 inches. So we're going to draw the box here. So when you're drawing your box, you may want to kind of make a little parallelogram across the bottom, and we can kind of I'm not the best at drawing those, but well, you get the idea. Alright, so that's our side. We can't see back there. Alright, so we have our little box, and it says here that the perimeter of the base plus the height, so all of these sides together plus the height, can't be more than 72. Now this one says that the base of the box is a rectangle with a length that is equal to 2 times the width. So I probably didn't draw this very well. Mine looks more like a square. But if the length is 2 times the width, so we're going to let one of these sides be x, and the other side of the base of my box here, this is the base, we're going to let the other side be twice that, 2x. So if this one's x, so is that one back there? If this one's 2x, this one is 2x. So if I add all of those up, 2x plus x plus 2x plus x, I get a base total of 6x. So if I had 72 to start with, and I know that my base total is 6, then 6x plus my height has to equal 72. So my height then would equal 72 minus 6x. So this height is going to be 72 minus 6x. So now I've got my length, my width, and my height. So for my volume function, I've got x times 2x times 72 minus 6x. Now, on your homework problems, this base, I believe, is a square. So all of these sides would just be x and a total of 4x. So just be careful about how they describe the base of your box. So at this point, we just type it in the calculator. It's going to be very similar to the one we did in example 1. All right, so we're going to type it in the calculator. So there it is, x times 2x times 72 minus 6x. And then I'm going to set my window pretty large on my y values because I know that I've got 72 as one of my numbers in the factors up there. And so I know that it's going to be large. So I changed my scale here a little bit as well. I made my x's a little bit larger. 10 may have been enough, but anyway, let's give it a look. So here we go. Okay. So what I see here, over to the left, it looks like it goes up. But again, remember this negative stuff isn't going to be super important to us. This one came down. It looks like it goes to 0, goes back up, and back down. But only where it is positive for x and positive for y is it going to be important to us. So we need to find where it intersects here. So second trace 0. Looks like that intersects at 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units out. And we need our maximum. So second, calculate the maximum. Left, right, enter. So 8 and 3,072. And I did by 250 going up, so it looks like 3, 4, 5, 6, 7, 8, 9, 10, 11, about 12. Now this one is offset to the right, so probably somewhere in here. Remember that it came in from this side, but then goes up, comes back down, and again it would continue down below, but that's also irrelevant to us. So this point up here was at 8, 3,072. All right. So it wants over here our solution, which it said find the dimensions of the box. So this time it doesn't ask for the volume. The volume would be the 3,072, but it just wants the dimensions that give us that volume. So remember that 8 is our x value. So this side would be 8 inches long. Then 2 times 8 are 16 inches. And then 72 minus 6 times 8, which is going to be 24 inches. So our solution is 8 inches by 16 inches by 24 inches. Our domain runs from 0 to 12, and our range from 0 to 3,072. Alright, and on this last example it says that we're going to make a box with a lid out of a piece of material that's 10 by 20 inches. And it says 2 congruent rectangles are removed from one end and 2 squares are removed from one end. And it says determine the value of x so that the box has a maximum volume. So I wanted you to, I know there's a diagram here, but what we're doing is cutting out these little squares right here from this half, because this is where half of the material is. This is the middle of the material. And on the other end, we're removing the whole rectangle here. So the side that we're removing the rectangle from is going to become the lid of the box. This is going to fold over. So I kind of created one for you so you can see what it looks like. So here's half of the material. And then here it is all laid out. So there it is. We're going to roll these up. We're going to fold these up so that we have the sides of our box. Alright, like this. So it's got a bottom to it. And then back here where this is dotted, we're going to make that the same height as the rest of the box. And that creates the lid that comes over. So it folds up on the edge like this. And then we have a lid that will fold down over it. So we have a closed box. So little box there. All right. So I wanted you to understand what we're doing. And it says that this material starts out as a 10 by 20 inch piece. So this is 10. This entire thing is 20. Well, we already know right off the bat that, the part that creates the base of the box is just half of the material. The rest of this is just the lid. So we're going to concentrate on this end of the material, which is now from here to here 10 inches long. And so this flap becomes, we're taking out again this little x amount. This flap becomes 10 minus x. This flap is going to be 10 minus 2x. And of course, again, the height, like our original problem, is just x. It's the amount that we cut out. So that makes our volume function length times width times height, or x times 10 minus x times 10 minus 2x. And just like the other two, once we have the equation set up, we can put that in our calculator to find our solution. Alright, so here's our equation, x times 10 minus x times 10 minus 2x. For my window, I went back to a smaller window because these numbers are not as large. So I went from -1 to 15 and -10 to 100. So let's see what we get here. All right, so it looks like my graph goes down over here, comes up, goes back down, goes down for a while, then comes back up. And again, this part, once we go to a negative volume, not relevant to us. So we're going from 0 to here. And that is 1, 2, 3, 4, 5. It looks like exactly 5, but we'll make sure. But about 5 marks over. All right, so I was putting that on my sketch. Let me show you what I just got down here. So let's double check that before I put that in. We're going to calculate the 0. There it is. Left and right. So it is at 5, 5, 0. And then we want to find that maximum. So I can calculate the maximum. Left and right. So 2.113, 96.225. So 2.113, 96.125. I'm going to go by units of 10, 20, 30, 40, 50, 60, 70, 80, 90. So 96, 2.13, somewhere in there. And the graph, of course, came up, but starting here is going to be relevant to us, came down, went down below and back up, again, not relevant. Okay. So this one asks us to determine the value of x so that we do get a maximum volume. So the x value that gives us a maximum is going to be this 2.113. So x is 2.113. And then it says, what is the maximum volume? So the maximum volume would be my second answer, and my volume is 96.125, and this is going to be cubic inches. My domain, it ran from 0 to 5, and our range 0 to 96.125. All right, so once you get your volume equation written, these are very similar to our area problems that we did earlier in the